pick up where you left off. All right. So we left off, we just got done talking about protein folding, right? So the 4 levels of folding: primary, secondary, tertiary, quaternary. Talked a little bit about motifs and domains. But now kind of to sort of extend the idea of folding, the discussion of folding, we get to the idea of chaperones, right? So basically chaperones are proteins that are involved in protein folding. So they're proteins that fold proteins that themselves need to be folded. So this is, if you're wondering, a lot of times it's not uncommon for students to kind of catch the circular reasoning there, the chicken egg situation. So how does a protein that needs to be folded be the one who does the folding of the proteins, right? Who folds the folder, right? That sort of a thing. We don't know exactly, right? This is kind of like, there's several different like chicken or egg situations in evolutionary discussions where, excuse me, where we don't really know how it all worked out, right? This is one of them. So if you need a protein to fold a protein, then who's the protein that's folding the protein? Or how does that original protein get folded? Right. So we just don't know, really. We've got ideas, we think. There's a bunch of different models out there, but when it comes down to it, nobody really knows what came first, the chicken or the egg, because there's good arguments for either. And those are like one of those soft spots that I always mention about in the beginning of the semester. Those kind of like evolutionary soft spots where there's some things we know pretty well, we're pretty confident about it, and there's some things we don't know so well, we're not so confident about it. This is kind of one of them, those chicken or egg situations. And there's like several of them, and then there's just enough of them to keep us honest about our raging egos getting away with us and thinking we know all the secrets of the universe. And so that's this is one of those, right? So let me kind of explain a little bit what we're talking about here, right? So the idea of a chaperone is so here's how we used to think about it. There's a little bit of a sort of a growth process associated with this, especially with like protein folding, and it's good reasoning. I mean, all of our ideas are, but often the most reasoned explanations are wrong still. So they make good sense, but they're still wrong. This is an example of one of those. So we just kind of had to sort of grow into our knowledge on this one. We kind of got it wrong a little bit at the beginning. But here's how we used to think about it. We used to think that protein folding was spontaneous. That is to say that a protein going from its primary structure, like its linear strand, to its big 3-dimensional globular protein, which is critically shaped, right? So Murray's shape and function for a protein are critical. They go hand in hand. And so if you screw up the protein shape, you're going to screw up its function, and it's going to be really tragic. So we used to think it was all spontaneous. That is to say, all you have to do is just hook all these amino acids in line, and it takes care of itself. And there's good reason to believe that, right? Because after all, think about it. When you take a look at the backbone interactions, right? That's the secondary structural level. Do we have to sweet talk those negatives on the oxygens and those positives on the hydrogens to find each other and to zipper up? No, typically an electrostatic attraction is fairly spontaneous, right? I mean, as long as they're within fairly close proximity, they can actually see each other. You don't have to do anything. They're automatically going to be attracted to each other, right? That's an automatic kind of a spontaneous sort of a thing. And so it made a lot of good sense that we would start to get some of the beginnings of this folding in a spontaneous sort of way. Not only that, but when we take a look at the temperaments of the R groups, right? Those side chains, those are also spontaneous, aren't they? Like the polar non-polar interaction Do you have to do anything for that one? No. What do they do? Are they attracted to each other? Polar, non-polar? They're very repulsed by each other, right? So do you have to do anything for that? No, that's automatic, right? So that's something you don't have to sweet talk them into. It's like spontaneous, just like you don't have to tell oil to form a layer. It does it automatically, right? So those are spontaneous interactions. I mean, they hate each other so much that they're naturally going to run away from each other. Remember the organizational power of water, right? So I didn't have to do anything. All I had to do is just stand in the middle of you guys, and you automatically were repulsed by me, and you ran to opposite sides of the room, right? The same thing's true here. So it makes a lot of sense. Even the interactions with the R groups are spontaneous interactions. If they're in proximity to each other, they have a natural visceral reaction to each other. So it makes a lot of sense, right? Initially, it's like, well, of course, there's a good, I mean, this is really pretty sound, actually. It's a pretty solid idea if you think about it, that this would be automatic, that you would basically, would you like bug me some other time? Anyway, so always like, oh, you're in class, I'm gonna like dump all this crap on you now, right? So basically, you have these like spontaneous interactions. So it makes a lot of sense that the folding would be spontaneous, that you just form your linear chain and then it would just basically start to spontaneously fold. Not only that, but we used to think that chaperones were basically the fixers. Now, what's a fixer? Got to think political. Right? What does a fixer do? By the way, every president has a fixer. Yeah, right. Somebody whose job it is to sort of sanitize a particularly difficult situation. Yes. So their job is to go pay the hush money to whoever's causing problems, or to smear somebody, and to basically sort of make them discredit them, essentially, right? So different presidents have kind of different takes on it. A good president, you will oftentimes never know who the fixers are, and different fixers will do different things. Some of them are kind of a wheelie dealy. They'll say like, listen, if you be quiet, we'll pay you whatever. Others are a little more brutal, like Clinton, for instance, was a master at smear campaigning, but in a aw shucks sort of a way. So you kind of liked him anyway, even though he destroyed people's lives, or his fixers did, not him actually, specifically. Obama had fixers, but his personality was so big that you never really actually paid much attention to his fixers. Probably the most obvious fixers is our last president, not the current one, right? I mean, he had his fixers going 24/7 because that was just a train wreck, right? I mean, there was a lot of fixing that needed to be done. And sometimes you'll hear them referred to as handlers, right? That's what President Biden's fixers are called. They're called handlers, right? How to coach or advise the president on matters of potential disaster and things like that. So basically the idea is, if you're doing well, right? And I like to use the president because we have a love-hate relationship with them. But if you're doing well, then generally speaking, your fixers shouldn't be needed very often, right? I mean, this was kind of the case with Reagan was pretty smooth. Reagan's fixers were pretty lazy. Carter, same thing, because he was just likable. He was a likable guy. I mean, he didn't do bad things. He still doesn't do bad things, by the way. So, I mean, if it's going well, your fixers should not really have much to do. And so that was the idea here. Right. So when we say the chaperones were thought of as the fixers approaching misfolding, the idea is like, well, things are mostly going well. And the spontaneous folding of these proteins is, for the most part, like maybe 80, 90% good, you know, like a decent president, somebody who's largely kind of keeping their nose clean and not screwing up too badly. And so the fix, for the most part, you're about 80-90% there. And then your fixers will focus on the other 10-20% or so. And just to kind of make it, manageable, right? Manageable disaster. And that was the way we thought about proteins. We thought that these guys were folding spontaneously, and then mostly they would get it right. Every now and then they would get it wrong. And then in comes the chaperones, the fixers, to kind of fix it. But for the most part, it was always thought that these fixers were largely a very minor sort of a situation. And so what they would do is they would come in here and they would help the proteins fold themselves correctly for those very small percentages that had a problem. Now, the idea with this is that essentially a chaperone would come in, they would kind of like smooth out the misfolded protein. And the idea is you just kind of let it go and let it refold. The chances of you misfolding the same way twice is remote, right? Because it's a random sort of a thing. And so you're more than likely going to get it right the next time. Okay. And that's the idea. However, all that went out the window when we started really learning about what chaperones do. And what we looked at was basically deficiencies of chaperones. A deficiency is essentially a deletion, usually in the chaperone gene, or the gene that encodes the chaperone. Now here's what, and this is the way we study stuff, right? Basically, if we want to know what it does for a living, what we do is we eliminate it from the scenario, and the absence of its function is something that we should be able to score. We should be like, oh, I see. So this job is no longer being done, therefore you must have done that job. Right? And that's kind of how we study the function of these sorts of things, is by eliminating that function and then recording that and saying like, okay, so this is what you did for a living. And so what we were expecting to see when we deleted these chaperones is we were expecting to see maybe a little bit of an uptick in the number of misfolded proteins, 10% maybe, 20%, but not a big chunk of it. What we actually ended up finding was actually an overwhelming amount of misfolding. We weren't expecting that, right? If you're a fixer, then the idea is you just are just working on just a little bit of it. So if we remove you and there's like an overwhelming amount of misfolding, that means you were doing more than just an occasional fix here and there. What that suggests is that you were actually part of the process. The normal folding process. So if you want to use the presidential idea, right, since we kind of know what the fixers are, this is a sort of a situation where it's like, oh, you're not just a fixer, you're actually more of like an actual full-throated advisor, right? So you're actually doing more than just fixing messes. You're actually advising the president on matters of policy that you're expert at or whatever. So you actually are a bit more part of the process, the normal process, not just the crisis management component of it, right? So that suggests then that there's a bigger piece of that. And we found this in cystic fibrosis. And cystic fibrosis is basically a disease where you lose a chloride channel. So the protein involved in cystic fibrosis is a chloride channel. And it's hereditary. But what we noticed in this particular type of cystic fibrosis was that when we analyzed the chloride channel, we noticed in this particular case, the chloride channel itself had normal amino acid sequence. What does that mean? That means there is no mutation in the CF gene. The CF gene is normal. So then why are we having chloride channel problems then, right? If it's so normal, then why is it not working? How do they know if it's the chloride channel is not working? So, or how they know that the sequence is normal? So the cystic fibrosis is an easy one because it's so tragic And the chloride channel is utilized in so many different organ systems that you have like a landslide of different symptoms throughout lots of organ systems. So it's a very easy one to actually diagnose, because the symptoms are like grabbing you by the throat. It's like, hello, nothing's working here chloride wise. And I've got these massive symptoms throughout many, many organ systems, not just respiratory. So there's like liver symptoms, there's reproductive systems, there's everywhere the chloride channel is needed, which is in a lot of different tissues, you're going to have a fail there. So this is interesting, right? Because they noticed that according to the genetics, there's not a CF gene mutation here. So this should be working fine, right? But what they actually found out was it wasn't the CF gene itself, but the CF gene actually failed to fold. Why? Because of your chaperone. So there was some critical, so the mutation was in a chaperone that was critical for the folding of the chloride channel. You lose your chaperone, you lose your chloride channel. That tells us, first of all, very straight and very, very clearly that number one, that the chaperones are not just fixers. Number two, that proteins cannot fold spontaneously, because otherwise there should have been no cystic fibrosis, right? If you have a normal sequence, you should have folded up just fine if it's spontaneous, but not so if you actually need a chaperone to kind of nanny you through the entire the entire process of protein folding. So if you're having to have a chaperone sort of escort you through primary to secondary to tertiary and so forth, then if you lose your escort, you're lost, right? And none of that, but that also says and proves that there's not sufficient information in the linear chain of amino acids itself in order to manage folding, which is the reason why you need chaperones. Okay. So this is how your chaperone works. So you can see your misfolded protein will basically come into this chamber, this active site where your misfolded protein will kind of come in there. You expend a little bit of ATP, which is your energy. You're going to cap it. Then you're going to kind of shake it up like a good mixed drink, right? So actually what's happening is the chaperone is sort of kind of unraveling the protein and kind of like massaging it, sort of the same way that you would knead dough. So you're just kind of like kneading it in sort of different shapes and things like that. And then the idea is like, as you sort of knead the unfolded protein, then it's going to find its correct connections and its correct folds. And then you're going to release that folded protein, and then you're good at that point. So the idea of unfolded protein is actually a really critical idea. And you actually have entire response systems to address unfolded protein. Because basically an unfolded protein is a functionless protein. It's kind of like, a human that's basically roadkill, been flattened by a semi on I-25 because you made the stupid mistake of trying to cross I-25 from the fast lane when your car breaks down. And then you become roadkill. Well, that's a pretty functionless person now, isn't it? The same thing's true here, right? So for us, three-dimensional shape is critical. And if there's an accumulation of dead bodies on I-25, then that's going to cause a problem, isn't it? So if you see a bunch of dead bodies on I-25 because there's like, a whole bunch of people trying to run across I-25, that's going to stop traffic, yes? That's going to cause lots of stress. And that's going to start, and what's going to happen? We're going to realize, oh, well, there's some sort of problem on I-25. So what do? We pull off and start using the back roads, right? But then what happens to those back roads? They start to get clogged up too, don't they? Now, all of a sudden, all of your plan Bs and plan Cs are choked up. And now you're kind of like in this sort of state of stress and gridlock. And nobody can go anywhere or do anything. And then think about this. From that global perspective, if everybody is stuck in a traffic jam and nobody can go anywhere, is business going to get done in Denver? No. So the functions, the basic functions of the city come to a grinding halt. Now, of course, that's a temporary situation, right? Eventually we'll clean the mess up, scrub it off the pavement a little bit, It'll probably be pretty gory, maybe a great AMP lesson, but eventually we'll clean it up and traffic will get going again, right? But what if it doesn't, right? What if it's more of like a structural thing? What if it's like not just a bunch of mess on the freeway? What if it's actual a structural problem? Like what if part of the freeway was just bombed out and you just literally couldn't get across it? That's not going to be a quick fix, is it? So the longer we stay in gridlock and we don't go anywhere, by the way, you can't call people to pick you up. Nope, can't do that. It's you and your car. That's all you've got. So the longer we stay in gridlock, the longer businesses in Denver start to shut down, right? We can't get anywhere. We're not functional anymore. We can't get to work and run the business that we need to run. So what happens? The business shuts its doors for a day, for 2 days, for 3 days. What if the crew takes a look at the road and figures we can't fix this? That 3 becomes 4, becomes 5, becomes indefinite. What's going to happen to the city of Denver if the people of Denver can't get to where they need to go to do business? Oh, we know what happens. Yeah, we just went through it, right? Only it wasn't traffic, it was COVID. So the entire economy collapses, right? I mean, we've seen this. How many businesses did you like appreciate and rely on before COVID? They're gone now. So basically everything disappears, everything goes away. That is the sign of a dying economy, right? Now, if you're a cell and all of you misfolded proteins can't get refolded again for some reason or another, then what's going to happen to the cell? It can't do its business. Why? Because who does the cell's business? You do. But you're misfolded, and there's no way you can't get yourself folded correctly again. So what happens? You just keep making more misfolded proteins, right? And then pretty soon we turn into a city of misfolded proteins. So we have no capacity to do work. We have no capacity to get anything accomplished. The city of Denver basically dies and turns into a ghost town, right? And that's exactly, now if your cell does that, then what's going to happen is your cell is going to die. And that's not a good thing. That's the consequence of misfolded proteins. So that's the reason why there's like an entire stress mechanism associated with the accumulation of misfolded protein, because misfolded protein is generally a bad thing. Christopher. Yeah, the chaperones are just a small part of the story. There's an entire response system that's actually even still a smaller piece of the story, but bigger than chaperones, called the misfolded protein response system. And what it does, it kind of like is a group of regulatory proteins that sort of manages and monitors how many misfolded proteins are accumulating. And then what it'll do is it'll activate and turn the chaperones on. So it's like, listen, we're kind of getting some misfolded proteins here. So you guys kind of need to start working on some of these misfolded proteins and get them all smoothed out. Now, if it doesn't work, if for one reason or another, those misfolded proteins don't get refolded correctly, then they accumulate and they start to form aggregations of protein, and that's bad, right? If you're wondering, if you form aggregations of protein because they're getting misfolded and they're not getting fixed with the misfolded protein response, then that starts to trigger stress signals. And those stress signals, part of that is cell suicide. It's like, listen, you're such a train wreck now. Denver is so like incapable of doing anything now. What we're going to do is we're basically all going to leave the city. And we're going to leave behind a shell, a ghost town. And everybody's going to go somewhere else. That's basically city suicide. Cells do the same thing. So if those proteins accumulate, they aggregate, it creates a stress mechanism that turns on in the cell. And part of that is cell suicide. the cell will basically die because of that. And not only that, but if one of those cells that are dying is a neuron, then you don't get that one back. And if you have that going on in multiple neurons, then you don't get those back. And if that goes into multiple regions of brain tissue, then you start to disrupt neural connections and you start to lay the groundwork for neurodegenerative disease. And you don't get that back. So that's the reason why, I mean, at its heart, actually in the honors version of 1111, there's a paper that we go over that goes in depth on exactly that mechanism. It's called the ER stress response that's tied into the misfolded protein component. And it looks at basically protein aggregation and misfolding as a mechanism for neurodegenerative diseases of all sorts, not just Alzheimer's, but Parkinson's and Huntington's and all sorts of different neurodegenerative diseases, which is kind of, it's a fascinating paper to read. But let's go ahead and jack around with the shape of a protein. Now, what we have here is the idea of denaturation. Now, denaturation is a loss of structure, and because you lose your structure, you also lose your function, right? The two of these guys are tied together, because remember, for a protein, three-dimensional shape is everything. Its shape is critical. So you're not just haphazardly putting this thing together in tertiary structure. It's like you're literally forming a specific shape, right? Think of it as sort of like making a piece of pottery. The shape of whatever it is you're making is very specific, and it's full of function, right? So like, for instance, if you make a teacup out of the clay, and like just a spinning wheel, right? So you kind of make a little teacup. It has to have kind of like almost like a bowl-like shape to it, right? If it doesn't have that shape, it's not going to be able to function to hold tea. You don't make a teacup flat like a saucer because it's not going to be able to hold your tea properly, right? So structure, the shape of it, is critical to its function. The same thing is true for proteins. Now, these three parameters, and there's three major things that will actually affect protein shape. The first one is pH, then we have temperature and salinity. Now, we're going to take a look at extremes, but in lesser conditions, to lesser extremes, will affect protein function, but not kill it. Remember when we went over buffer, where we said that the enzyme was active as long as it stayed in that 4 to 6 range? So that's a good example of a pH, right? You're changing pH. But remember, when you went out of the 6 range, the enzyme, you didn't denature it. It just was suboptimal. It just wasn't in its perfect environment, right? So you just change the circumstance. It's kind of like you guys. Right now, we're at room temperature. It's pretty nice. You guys are pretty productive, right? But if we were to basically turn this room like to minus 30, would you guys be as productive? No, because all you'd be thinking about is staying warm, right? So you wouldn't be getting a lot accomplished. Now, would I be killing you? No, you'd still be alive. You'd just be really cold, right? But I didn't have to kill you to make you non-productive, right? Now, I can kill you if I really just like expose you and you get hypothermic and then you die, right? But I don't have to. If all I'm going is for you to not be productive, I don't have to kill you. If I go extreme, like denaturation, I will kill you. Kristen. So the idea of using an ice treatment, regardless of what it's for, is always the same, right? Because the idea is everything slows down in cold. And so that's what you're trying to do. So you're trying, usually it's swelling is what you're going after. But that all slows down when it's cold. and it increases when it's hot, right? Which is one of the reasons why you kind of cool yourself down, is to sort of slow that down so that the swelling doesn't become an impediment to normal function, right? That's when you do it. And so that's the reason, but that's always the case for all cold treatment, is you're usually trying to slow down some sort of a physiological process that's kind of spinning out of control or has the potential to spin out of control. And the opposite is true for heat treatments. That's basically where you're trying to increase the flow so that you can accelerate the response, right? And this is oftentimes why you'll get an initial cold treatment to reduce the swelling from sort of spinning out of control and becoming a physical problem, right? But then you'll kind of get to this point where you're kind of doing alternations of hot, cold, hot, cold. So you're trying to keep the swelling from getting out of control, but then you also want to keep the blood flow going so that all of those cells that need to get to that point of injury to fix things can actually get there quickly. That makes sense? Is that a sort of a half hand going up? Yeah, so if they're like, basically if the machine is doing the work for you while they're doing heart surgery, and they kind of have you basically living off the machine and they cool you down, that's exactly what they're doing. Because the idea is your body, what they want is they want to reduce the demand for blood and for oxygen. And the only way that you can do that is by cooling down your tissues so that everything is slow. All your metabolic rates are slower, and so their requirement for oxygen is slower. And that kind of reduces the demand on the heart to actually give them oxygen, and that kind of keeps that sort of under control for them. So you don't have like this raging, screaming demand from the body saying, I want food, while you're trying to fix the feeder. That makes sense? And that's the reason why they do that. It's very similar to like a situation where, like, if you drown in cold water, you have a better chance of survival because the cold water slows all your metabolism down and reduces your need for oxygen. And so typically if somebody does survive drowning, even like after ridiculous amounts of time underwater, it's usually they were in cold water. And they may lose a few limbs or something like that due to frostbite or whatever. But it's like their cardiovascular system was able to, that demand was able to slow down enough so that you didn't need as much oxygen. And that's really the reason that you drown. You don't drown because water is liquid. You can breathe liquid just fine. The reason why you drown is because there's not enough oxygen in water to sustain your metabolic needs. If there were, we'd be able to breathe water without a problem. There's nothing about liquid that is causing a problem with drowning. So it doesn't change the way it's folded, but it does change its behavior. And actually in AMP, and this is where Melissa's getting these questions from. So one of the things you realize that when you kind of get in that section, it's usually in the respiratory section of the system. What and all enzymes have when they're folding up is what's called affinity, which is how tightly they bind to their substrate, right? Now, hemoglobin is unique because most enzymes bind very strongly. They're like toddlers with a toy, mine, right? But hemoglobin is very unique in the sense that it both binds to oxygen with great affinity, but it will also release it. So it can actually toggle back and forth between states of high affinity and low affinity. And one of the things that actually affects how strongly hemoglobin binds to oxygen is temperature and pH. Both of those will affect hemoglobin. So you can actually cause hemoglobin to either hang on to oxygen more tightly or to release it more readily, depending on how you play around with temperature. And that would also factor in to the cold water drowning situation, because not only do you have reduced demand in the tissues, but then you also have a change in the affinity of hemoglobin to actually release that to the tissues in the first place. Okay. So let's take a look at some extremes. Let's kill them. So these are kill levels. So now we kind of know how to, we get a sense of how to sort of change the behavior of an enzyme with slight changes in pH and things like that. A very, very common trick your body plays to regulate how enzymes act. But let's go ahead and do the extremes, right? So this is going to be extreme. So if you have extreme pH, this will unravel a protein and kill it. An example of this one is make cheese with lemon juice. Any cheese makers in the crowd? Have you ever made cheese before? It's not a difficult process. Generally speaking, what you use is you have to start off with a good source of milk, right? Oftentimes back in the day, it's raw milk, right? Straight from the cow. Or you would probably at least want whole. But the idea is you want all those milk fats and proteins and things like that. So you don't want that stuff skimmed off, right? No skim milk here. That's not going to work out. And so what you do is oftentimes in cheese making, what you usually do is you'll use an enzyme called rennin that will essentially curdle the milk. Now, the problem with rennin is it's an enzyme that comes from sheep gut. And so a lot of times vegans will have issues with that animal source, different non-vegans actually. If you're a vegan, you're probably not actually worried about cheese anyway. But if you're like a lacto-ovo person, then, you know, and you just want to stay away from the sheep gut thing, right? Because you'd have to kill the sheep to get it. That's kind of the idea. So you're a philosophical vegan as opposed to, you know, I guess what would a non-philosophical, I don't know what the alternative of that would be, but right. So obviously I'm not a vegan, so just go with it. But anyway, right. So in this case, you'd kind of want to, they call it vegan cheese, basically sometimes in the store, that's what they're talking about. But what is the pH of lemon juice? Remember this one? You lemon lovers? Yeah, 2, right? So it's like right down there with stomach acid. And so what you do is you basically take your milk, your whole milk or your raw milk, and you add lemon juice to it. What happens is the acid basically unravels all the milk proteins and they get tangled up and they become this sort of coagulated mass of mess. And then they kind of capture the milk fats in there and the sugars and things like that. And it becomes basically these chunks, right? Better known as curds, right? And then the liquid, the non-chunky part, is the whey. So when little Miss Muffet sat on her tuffet eating her curds and whey, what was she eating? You guys have all seen this in the store. Some of you like it. Cottage cheese. She was eating cottage cheese, right? That's basically what it is, because cottage cheese has the chunks, the curds in it, right? That's the coagulated part of it. And it's got the liquidy part of it, right? That's the whey. In cheese making, then all you do is you take cheesecloth, you sort of strain out the curds, you press it on a cheese press, get all that, and you kind of get it as dry as you want. If you want a fairly wet cheese, then, you know, you don't press it so much. If you want a really dry cheese, like a gradable cheese, then you press the devil out of it. And then you either wash it with some sort of a brine or a bacterial wash or something like that, and then you let it age. Any kind of an acid would work. So, and a lot of times, like in a vegan cheese, you won't use lemon juice because you'll still taste the leftover lemon flavor from the lemon juice itself. So in some like commercial outfits, they'll just take like sort of a non-obvious taste type of an acid that kind of disappears in the matrix of the cheese. So you don't really taste the denaturer, you just taste the cheese. But that's an example of a pH denaturing a protein. By the way, for those of you, there's a more disgusting version of that, like a toddler who's sick, who makes the mistake of drinking milk, and then out back it comes. No, 2 is typically, Yeah, 25, is that too late? It's like, I have to admit, I don't get a lot of breastfeeding questions in general bio. AMP, maybe, yes. General bio, I don't usually get a lot of them. Nice. No, there's a lot, there's many opinions about that. Generally speaking, like it's like the baby will start to give you signs when it's ready. So it's like starts to become less interested. It becomes more work to try to get them to nurse, and not only that, but I mean, they have to be able to actually hold down baby food. So there's like a transition area as you're starting to move them from breast milk to food itself, and you don't want to wait until 5. I mean, that's just not good, because as great as breast milk is, it's not designed to have the nutrients associated with the need of an older body, which is the reason why oftentimes, definitely like within the first year of going, but then as the child, and the different kids are different, right? Different babies are different. As they start to sort of take to just a little bit of baby food, like you just kind of try them out, you just let them experience it. It's an experiment at first. It's like, oh, here, just taste this. Do you like that? Bananas usually is where it starts, right? Because everybody loves bananas, right? And as they like it, then they start wanting that more. And then they kind of start, and you kind of go through this transition zone. And the idea is, as they start to gravitate toward that, you want them to get on the normal food as soon as possible, because they're going to need the extra nutrients in that food in order to support their development, because the mother's milk is not designed to have that much nutrients to it, right? But there's, I mean, if you talk to different doctors, they'll give you different opinions. There's some will be like, you don't need to breastfeed at all, right? And there's others will be like, you got to be at least a year, 2 years, 5 years is a little on the long side. That's when the eyebrows start going up, because like, wait a minute, your kid can vote already. I mean, so it's getting weird now, right? So that's, was there a question over here?
Well, I was just gonna say that it would also make sense, like, because if you're just breastfeeding one child, then you can't support another child, which in the continuation of the species sort of aspect is not optimal. So like getting that first child like out and off so that you can have another child.
Yeah, you want to get the first one settled before you get the next one in the pipeline.
But you still need a next one in the pipeline. So.
Yeah, so that's the reason why we have one at a time, generally speaking, right? So.
Yeah, well, I have 3 kids, but with my first one, so I had breast milk until I got pregnant, and the first one was just like completely, I didn't have to do until like I gave birth right there and then, like breast milk was back to clear from the body. So, at least for me.
Yeah, and that's, I mean, because that's another thing, right? Because the mother's body is that, especially with lactation, I mean, that is like a positive feedback loop, actually, that's maintained by the baby. And that is really a very dynamic and adaptive like communication between the baby and the mother, which is the reason why different babies are different, because they'll kind of send different signals. So the more they feed, the more signals they're sending to the mother's feedback loop to make more milk. And there's just that reinforcement. So as the baby starts to transition or starts to want more like baby food, then it's sending fewer signals to the mother's body to lactate. And so you kind of see this overall slowing of milk production. And milk production is very different. It's very variable amongst women. Some women are just boom. I mean, just a gangbusters. It comes in like right after birth, and it's just it's going. And others, I mean, it's a struggle. It's just a struggle, and it takes some time, and it's very, very variable, and it's one of those really dynamic systems that has a lot of moving parts to it, and the baby's part of that. So
how it kind of works with dairy cows too, right?
Mm-hmm.
Like your constant demand for the milk, like the constant milking is what keeps the production happening.
Yes, and among hormones as well.
Well, that is.
Yeah. Yeah, that's where the hormones come in with dairy cows. Is you give them hormones, you cheat. You give them hormones to basically stimulate lactation, whereas in humans, it's all about that feedback loop. I would argue that had nothing to do with the actual breast milk itself, because breast milk is fairly straightforward. I mean, it's fatty, so it's giving that nutrients to the baby. But the key piece of the breast milk is the antibodies. So really, it's not just nutrition for the baby, but it's actually immune defense, because a baby comes into the world without very much of an immune system, which is the reason why we are so cautious with babies and keeping them, like, away from stuff. But they get their first immune vaccination, if you will, from mom. So all of the diseases that mom went through, her entire pantheon of antibodies that she's collected over a lifetime, she's loading into her breast milk and giving to the baby itself. That's giving the baby some immune shelter that then allows it to be able to be healthier. And that's actually probably the number one primary component to breast milk, right? Because nutritionally, we've already been able to replace it with formula. And a lot of the formulas out there are pretty good for nutritional purposes, but nothing can replace that immune shelter that mom gives to the baby. And that is the biggest critical thing. I would argue that going long has nothing to do with breast milk, but it has more to do with the bond between the baby and the mother. And that the stronger that bond is, there's more of just like that visceral kind of, I can't even explain it. It's like guys don't get it. Mothers do, right? There's almost like that. It's like almost like a telepathic, like a connection between the mother and her baby in a way that transcends anything in experience. And that would be accentuated by a longer period of time. Because if you think about it, when you're breastfeeding, that's kind of like mom and babies, like that's their little alone time, right? That's the time when they are just like connected, and it's like a Vulcan mind melt. It's like that's just you, like soul to soul. I mean, you're just locked in there. And that would be conducive to laying good groundwork for later learning. Okay. So I would argue it has something more to do with that than the actual breast milk itself. Okay, so temperature. Yeah. Sorry.
Some animals need like their mother's like milk to be able to like consume like their main diet. Because I think it's like koalas, like if they don't get like a certain amount of their mother's like breast milk,
Yeah.
something like that, they can't eat at all.
Yeah, and that's until they're, because remember, most of your organs are there when you're born. The main system that's underdeveloped is your respiratory system. And then your digestive system is still also trying to get itself online, which is kind of where that early, like when you're talking about a newbie, like a newborn, that's when that breast milk really becomes critical, because mom gets to sort of screen all the nutrients and then sort of get that into the baby in a much easier sort of way. Wow, we're already at our witching hour, aren't we? It's a great, I spent like, how many hours did I spend on slide 32? That's good though, see, but that's helpful, right? Because that's like applied biology. I mean, when you're talking about lactation, because obviously, if you're a woman and you have a baby and you want to nurse, and that's a big decision, right? Do I want to do the nursing thing or do I want to do formula? I mean, that's a really big decision. There's a lot of big decisions when you have a baby, and the dudes aren't off the hook, right? Because the dudes also have a role to play in this one. Granted, we're not going to be nursing the babies, but I mean, hopefully if we're not a deadbeat, we're going to be around making sure that everything is going well, that mom and baby have everything they need. Right now, if you plan on being a deadbeat, don't tell me.
You ever hear about Boris Johnson's experience with breastfeeding?
Yeah. Boris Yeltsin. First of all, just mentioning the name makes me want to laugh, but no, I didn't. I don't know that I want to actually